Good day, this is Jamal, and in this video, um, I'll present my result on the 3 by 3 magic square of squares, you know, and this video is intended to be a video presentation of my results, which is handwritten for now, and at a more at a favorable time, this result will be documented in a research paper, and uploaded to the right channels. And so, yeah, so a brief this description of what a perfect cuboid is. It's a box, a grid with nine distinct um, sides on nine distinct unknowns, which would ideally have to be solved for integers. You know, so you could think of it as a as Rubik's cube. Looking at the Rubik's cube from one side of a Rubik's cube. How you'd be seeing nine different grids, pretty much the same fashion. So we'll just share the screen, you know, and yeah. So let's see. Yes, also a great website by Christian Boyer, which has also a lot of great information on the magic square of squares, and the- uh, mm, yes. So this Wikipedia, this is just a brief of a little bit of reading work. So it's an unsolved problem with regard to this problem, which is being able to construct a 3 by 3 magic square of squares from nine distinct integer squares, you know. So when you look at this definition, uh, parallel to my result over here, you'd find that this is basically what they're describing, this is just, a handwritten work. So a grid of this side with nine different, sides to solve, nine different unknowns to be solved for, you know. And so in this paper would, this video is the beginning of a series of a few videos where I'll be sharing my results on this problem incrementally. So for this paper, for the results we've been able to have, we have had um, a formula. The formula that have been developed for this in my results is such that um, we have eight integer formulas or eight integer solutions out of nine possible integer solutions, with the only non-integer being e squared as we have it, and there have been six working sides: one, two, three, four, five, and six, as I've had it in this paper. So this is a brief oversight, a brief overview. And so the goal is to, have all sides, this, 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 and that being equal to the same constant number, you know. And so this is as I have expressed. So we are supposed to get eight different possible integer sums. So one, two, three, four, five, six, seven, eight possible integer sums. And so this is how I approached it. So I took this side and took that side, and we find out that these two sides have the same unknown of A in common. So if you are to, subtract, you'd find out that you have d squared minus b squared plus g squared minus c squared. And when you try to, work out the math stuff, you get as a first equation this. And when you consider the second side, the second, which is taken, so the first thing is we took this and this. Now we're taking this and this. So we have this and that. And you find out that they have a common terms of g squared canceling out if you subtract. So we have this. And so now, as you have seen so far, we have now been able to link this to that and this to that. So in a natural order, We have to link this to that, as we see over here. And now we find out that they have I squared as common terms. So they cancel out, and we have these three different equations, three different equations as we see it, you know. So one might ask, why not pursue this and this and that and that, and why already initially pursuing the edges? So the goal is that when you work around the edges, you're able to easily get a constant term. You're supposed to, it's much easier to get a constant values, as in when I talk of a constant sum, it's much easier to work these things out in such a way that you have uh, this being all equal to the same number, and afterwards, when you decide to now look inward, whatever from whatever we're able to deduce out of that, we can then equate it to whatever constant sum we've had in the, for example, n. You know, so if I'm going to explain this in much understandable stem, we find out that if once we're able to work around this properly, we can be able to easily get a formula for n, where n is the sum of a, d, and g, a squared, d squared, and g squared. And not just that, likewise all around the edges. And whatever formula you can get for n, you know, if it is indeed constant and indeed constant, once we can easily, equate whatever we have by going this and that, or this and that, as far to whatever constant value we have here. So now this is the formulas you've been able to have, you know. We further linked a, b, and c squared to, yeah. So there are four equations now. And so, yeah, if you observe these four equations as we have it, you find out that b squared is equal to g squared. Sorry, b squared minus d squared equals g squared minus c squared. And when you come here, you find out that g squared is equal to f squared minus a squared. And so you come here and realize that we can suppose that b squared minus d squared equals g squared minus c squared. And this is also equal to this, and it is equal to some number, x, you know. So in this sense, we agree that whatever value we get for this and this and that should be the same number, which we labeled x, where they are all positive integers. Our target are positive integers. That's traditional group for any magic square of square, in a standard, given a standard definition, And so, yeah. And the goal is to ensure that all surrounding four equations work first, like I earlier discussed, And so, also, when we come, you also realize that just as you've been able to realize that this equals this and equals that and equals that, we have this being equal to this, and this also being equal to this, which is why we also have this, So the goal now is whatever we're going to do in the next second page, it's to, be able to express B, D, G, C, F, H in terms of X and their respective divisors, And then based on the formulas we have for all of this, we'll be able to, based on that, to calculate the formula for I squared and E squared. So that's the idea. So when we come down here, we equated this to that. And these are the formulas we had for B and D, And in this sense, R squared, R sub squared 2 is a divisor of X. It divides X, So if you have to consider the fact that, let's just continue. So when we come down here, you realize that R sub squared 3 is also divisible by X. So the goal is to, understand that this R sub squared 3 represent divisors, a divisor for which X an integer, for which you have C as an integer in itself, Likewise, G as well. R sub squared 4, as we see over here, is a divisor for X, for which you have F and H as an integer, and based on our formula we have for A squared equals A squared minus I squared equals F squared minus B squared. We come here and realize that here, this f squared minus b squared as we have it. Now, looking at the nature of this equation, we find out that, or we come to realize that a is positive, I squared is also positive, and the difference between the squares of two positive squares, as long once they are not different, they are distinct, we should expect to have positive values for whatever this number is. And to ensure that is the case, you have to realize that the smaller the divisor of a number, the bigger the number. So this tells us that we have to reduce the divisor of x over here. We have to make sure that r subscript 4 is smaller than r subscript 2. And by doing that, we realize that whatever value we have for this is bigger than this. So when you take the difference of these two numbers, you get a positive number, a positive whole number. And the same standards apply here. And so which was why we now see over here, as we stated over here, that this is the case for equation 5. Now we consider an example case. Let x be 2000 and represent r subscript 4, which is 2, and r subscript 2, which is 8. So we now realize that indeed 2 is less than 8. So when you substitute that into equation 5, which is this, realize that we have this over here, and that gives you a positive number of this. And we did that for equation 6. We had this number, and we did further calculations, further working of this one, and we were able to get this, and so now, and we're able to get this formula for I, and I is an integer. So now we have to understand this r subscript 5, it's a divisor of this whole entity, not x. And in natural sense, just to ensure unambiguity, I was supposed to have denoted it by different unknown, but I mean, once it's in print, we'll do something about that. And so this is the formula we have for I, and the formula we have for E, yeah, and this result, and for if if we wanted to prove this simply, we could simply prove it using simple induction, to prove this. So yeah, we now use a different. We now suppose that r subscript 5 was equal to 10 as an example to see what happens. So so after giving this example, and this example is just a continuation of the previous example over here. Yeah. So in this case, x was 2000 as we did before. R subscript 4 is 2. R subscript 2 is 8. And R subscript 5 is 10. And we make necessary substitutions, you find out that this is a formula, this is a number, the value we get for I, this is the value we get for E. And this is a list of values which we've had. You get it? And so this is a simple magic square of score we've been able to construct. This is a simple 3x3 magic square of squares you've been able to construct. And we realize that the E squared over here is a non-integer. That's the only non-integer. When you take a square root of this, you get a third, which is the non-integer. Yeah. So this is just an example. This is just an example case we considered. And once it's a formula, it works generally. I'm not saying it's a general solution, but I'm just saying that this idea just works. This idea just works. And so if you were to add this to this plus this squared plus this squared plus this squared, you get the same number as adding this and adding that and adding that, and adding this and adding that. The only ones that don't work is this and that. These are only the two. It is only the two diagonals that does not work. So far, when you come down here, yeah, you find that and the discrepancy over here comes from this addressing this ones. That's just that, and even for this one, you'd find that even for the when you consider these two equations, let's consider these ones. Let's come here. Let's see something. Yeah. Um. Yeah. I mean, this already works. This one already comes from here. This one already comes from this and that, so it automatically works. And using this approach and dwelling on this one is much easier to get a constant value for e squared. You know, but as I was saying before, the discrepancy comes from here, this particular one itself. And yeah. So the idea is that if I mean, this is an idea I'll try out. This is the idea I'll try out if you're to expand this onto a much more general case. That would be to solve this and solve that simultaneously and see what happens. That would be the best way to approach a much general case of this problem. But as of now, this particular video I'm recording is meant to cover the case where we have 8 out of 9 integer unknowns out of possible 9 integer solutions and 6 good possible sums out of 8. And so these are the good sums we've had so far. These are the good sums, and these are the bad sums. You know, so these are the result. These are the results we've had. And yeah, like I earlier said, the divisor R subscript 5 is used to denote being a divisor of this term. This particular term. Which is of that of a squared minus I squared. Yeah. And so I do intend to replace this particular notation. So maybe in a print version, I'll not use R subscript 5 because to use R subscript 5, I'll be therefore implying that it's a divisor of X, which is not accurate. Then what we mean here is that it's supposed to be a divisor of this, and whatever this number is, it should have poss possibly different devices than X in itself. So yeah, and so yeah, so coming to considering equation 8, and at this point, uh, we've been able to determine that R subscript 4 should be lesser in size, should be smaller than R subscript 2, you know. But what about the divisor R subscript 3, you know? So in this sense, given the ordering of devices as in page 2 over here, this is what I mean at ordering. When we look at the left side of the equation, when you look at this particular side of the equation, uh, if once both sides are positive values, since this is a positive number, this is a positive number, distinct positive numbers, their squares should be positive. We should have a positive number here, have a positive number, and to ensure we have positive numbers, the divisor R3 has to be smaller than R subscript 2. Why? Because the smaller the divisor, the bigger the number, which is basic math over there. And so for visibility, just to make things a bit lucid, we group the terms with constant operation signs. So those the plus operation signs are here, and those with the minus operation signs are here. And so over here we see that to ensure this is positive, R has to be smaller than R subscript 2, as you have labeled over here. And the proposition here is that if R subscript 4 is less than R subscript 2, and R subscript 2 is less than and R subscript 3 is less than R subscript 2, then R subscript 4, which is and should be lesser than R subscript 3, should be lesser than R subscript 2. And all these R's you see over here, like I said before, are all divisors of X, this particular X as we dealt with before, you know. And so over here, given we have been able to deduce these formulas for the unknowns, we will express n, and the n is a sum of the constant sum. We'll deduce this in terms of the formulas we developed above. And so in this sense, we have this giant formula for a squared and b squared and c squared, you know, and given this formula, you could simply so when you subtract b and h, b squared minus h squared from this from n, you get this formula for e squared, and so this was what I tried to denote. This was what we tried to you know indicate earlier that we had sums working for this side, constant sums here, constant sum here, constant sums here, constant sums here, constant sum here, and a constant sum here. The only ones which were not constant were these and that, you know. So yeah, okay. So yeah, so I don't intend to make this video a very long one. I just made this video to share my result as I've had it right now, and yeah, and like I said, at a more favorable time, as time goes on, at a more favorable time, which will not be very long from now. I will type this into standard, research paper, you know. And so in the next video, the goal would be to, explore or dare to explore a more general approach to this problem. And then, yeah, we take it off from there. So thanks for watching and thanks for your time. Bye. Ciao.